is a very simplified geology of this part of the Craton here, and the Carajás mineral province is right here in the eastern part. Carajás mineral province consists of two domains. The southern domain is called Rio Maria domain. The northern part is called the Carajás domain, where we're going to remain for the rest of the stroke. So the Carajás mineral province is, it has as limits, the northern limits and the southern limits are Paleoproterozoic 2.0 gigayears volcanosedimentary sequence, and towards the eastern side of the Amazon Craton, what you have, it's a large sequence of felsic volcanic rocks, and then with a series of granitic intrusives, and followed by a plutonovolcanic sequence here and volcanosedimentary sequence right in the western part. The metallogeny here is quite diversified, particularly with gold and copper gold. These are magmatic hydrothermal systems, but you do also have some other types of deposits, but the IOCG systems are actually here concentrated in the Carajás province. As any mineral province in the world, Carajás contains several metal commodities. So it's quite well known for the large ion formations. We are the second largest producers in the world. Also manganese, and then nickel and PGE associated with mafic, ultramafic intrusions, gold, copper gold, and then what we are interested today, the IOCG systems. Going to the geology of Carajás in general terms, what we have here, it's a basement with gneisses and migmatites, together with granulites and granitoids, all of Mesoarchean age, older than 2.8 gigayears. And on the top of this basement, there is the green stuff here represents a large volcanosedimentary sequence of Neoarchean age, 2.76, 2.773. It's called the Rio Itacaiunas or Rio Itacaiunas supergroup. And overlying this Neoarchean sequence, there is another one, this yellow one here, which is nowadays interpreted as a Paleoproterozoic siliciclastic unit, which is right there. In terms of magmatism, in the Neoarchean, we do have these synkinematic alkaline granites here that are coeval or late in the Neoarchean, and together with poorly constrained and they do not outcrop quite well in, regionally speaking, the 2.56 granites. And finally, A-type Paleoproterozoic granites, which are here represented by these red intrusions here. We have a cluster of IOCG deposits here in the southern part of Carajás. We call it the southern copper belt, and a series of deposits as well in the northern sector of the province. In terms of, this is just a very simplified stratigraphy of the sequence with the volcanosedimentary sequence that I talked about, the Rio Itacaiunas supergroup, which is basically Neoarchean, which is on the top of the basement, which is Mesoarchean, and on the top of that, the siliciclastic dominated sequence with several names here, and probably of Paleoproterozoic age. Well, the tectonic setting for the particularly for this volcanosedimentary sequence here of Newarkian age, is still controversial. We do have two main models. One, it's a continental rift system. The other one would be a back arc setting or a back arc scenario. The first one has been more popular at the moment. In terms of copper systems, we do not, Carajás do not have IOCG systems only. IOCGs may be perhaps the most important in economically speaking, but these are not the only types of copper system that we have in this province. We do have IOCGs, yes, okay, some of them with rich in nickel or in cobalt or in zinc, but they are IOCGs, and they've been in place, particularly in the Newarkian at 2.7, at 2.56, and they are Paleoproterozoic as well. So we have multiple events of IOCG emplacement in the Carajás province. But it's not only that. We do have a series of systems which have nothing to do with the IOCGs that we broadly call it copper polymetallic or granite related copper deposits. So with this, it's copper with a series of metals associated with it. Mostly they tend to be of Paleoproterozoic age. Well, Carajás has had from the Newarkian to the Paleoproterozoic a very complex history of deformation. And at the end of the day, what you have is this set of large-scale structures, brittle, ductile shear zones that actually they operate as the pathway for large-scale fluid flow as well as magmas, and most of them, particularly those that are nearly east-west, control most of the copper systems, particularly the IOCGs here in Carajás. I do have here the resources, the total copper endowment for Carajás, but this is a very conservative number, larger than 4 billion tons of ore, 0.9 weight% copper, 0.2 grams per ton of gold. But this is very conservative. It's not updated at all. As I told you, the Carajás, most of the IOCGs in Carajás are concentrated in the southern belt or in the southern sector and in the northern sector. So what I'm going to do is it's a trip to some of the deposits and show them and show to you their main characteristics. Okay, so I'll start with the deposits here in the south, and then I'll give you some examples in the northern sector. Here in the south, most of the deposits are or have a Newarkian age, but it's mainly 2.7. In the northern sector, most of the deposits, the age is 2.56. In any case, the two sets of deposits are Newarkian. And then I'll go and compare with the Paleoproterozoics. So first of all, southern sector, 2.7 deposits. These are some examples of these deposits. Some of them are very small, but some of them are world-class. And I'll concentrate my example, my study case in this mine here called Sossego. This is part of the geology of the southern part of the belt. And what you see here is a set of granitoids, Mesoarchean or Neoarchean. These are the granitoids. This is part of the volcanosedimentary sequence, which is Neoarchean. And throughout this area, you have several IOCG deposits. There is one mine here called Sossego that contains two main ore bodies, Sequeirinho and Sossego. I'm going to be talking about the Sequeirinho part in particular, as a representative of these 2.7 IOCG deposits in the southern sector. But regionally speaking, well, most of these deposits, they are structurally controlled, particularly for these regional lineaments, regional shear zones that I already showed you. It's always in regional terms here, what you see as far as hydrothermal alteration is concerned is a regional sodic and sodic calcic alteration. This alteration tends to be regional, tends to be distal to the main mineralized sites. For example, here you have a granitoid, and with all these anastomosing sets of whitish stuff, which is composed of albite and scapolite, or here zones rich in scapolite or zones rich in albite and actinolite that would represent a sodic calcic alteration. This tends to be structurally controlled, but tend to have a regional extent. Well, this is just a cartoon or a diagram showing the main alteration patterns that you see in these deposits in the southern part of the belt, these 2.7 deposits. So regional sodic and sodic calcic alteration, which is then near the mineralized zones or more proximal to the deposits, being replaced by calcic or calcic ferric alteration. This alteration here may in some deposits host the mineralization. Most of the mineralization in this case are magnetite rich, but some other deposits, this alteration evolves towards a potassic ion alteration, either represented by biotite or K feldspars, and this alteration may also involve mineralization, particularly breccias, and they may also evolve to a hydrolytic lower temperature alteration with chlorite, epidote, cerussite, carbonate, and magnetite. I'm not saying that all the deposits that you see here that are examples in the southern sector, they show the complete set of alteration. I'm not saying that. Some the evolution is here, and some others stop there. So I'm going to give one example because I just have 20 minutes to talk to you. And this is the case of the Sossego mine. It's a world-class deposit. It's still in operation. There are two major ore bodies in this mine. One is called Sequeirinho, is right here. The other one is Sossego. Let's concentrate on this one. And then I'll be talking about that one later. So let me just concentrate on this one. Note that the host rocks are granitic rocks of Mesoarchean age, gabbros of Neoarchean, of Mesoarchean age here, of Neoarchean age there. This is the ore is structurally controlled by this northeast striking structure, which is a second order of these regional scale east-west britoductile shear zones. So what I'm going to show you is the hydrothermal alteration that you see distal to proximal to the mineralization, okay? And starting with the granite here. There we go. So this is the Mesoarchean granite. Now it's pinkish because of sodic alteration, which is more regional. And this is, and as you go towards the mineralization, this alteration, the sodic alteration is gradually replaced by actinolite and epidote and albite, a sodic calcic alteration, which, and gradually this sodic calcic alteration is, and nearby the ore zones are strongly altered or replaced by a calcic ferric alteration. Ferric because there's a lot of magnetite here, calcic because you have a lot of actinolite is in these zones. And this calcic ferric alteration in this particular case involves the mineralization, involves the breccia, the chalcopyrite magnetite rich breccia. Note that in this case, the potassic alteration, either with biotite or K-feldspar, is poorly developed. The mineralization, it's dominated by chalcopyrite, pyrite, some nickel cobalt bearing sulfides, and a lot of other minor phases that are not uncommon in these IOCG systems, including gold, of course, and gold here in this case is hosted within chalcopyrite. A lot of apatite here, and so on and so forth. This is sygennite, or the nickel cobalt bearing sulfide I was talking about. Chalcopyrite is dominant, pyrite is there, and so on and so forth. So just to show you the age of this deposit, just to confirm that it's Newarkian, it's around 2.71, 2.78, the age of the mineralization, which is based on a geochronology of monazite and of rhenium osmium dating moly. Now, so if we now go back to the same area in the southern part, we were here. We were here in the Sossego mine, particularly here in this ore body called Sequeirim. I told you that regionally speaking, sodic and sodic calcic alteration is very common, affecting all the lithotypes in the region. But as you go towards the mineralization, as I showed you, you have calcic, ferric in this case, but in other cases, in other deposits, potassic, ferric, in other case, sodic, calcic, and so on and so forth. So it all depends on the deposit scale, evolution, and fluid rock interaction. Note also that it's not only copper gold. Some deposits are anomalous or very interesting concentrations of nickel and zinc as well. Now, we were down here, and now we can move upwards or northwards and see one example of one of the Newarkian deposits. Now the age is 2.56, and the example is Salobo. Salobo is the largest deposit or IOCG deposit in Carajás. It's in operation since 2004, if I'm not mistaken. And so it's a very large deposit, a world-class one. But there are others which are not in operation yet. They are in the pipeline, but they're there, such as Furnas. And there are some others here, such as Igarapé Bahia, and so on and so forth. Note that here, whereas in the southern sector, the host rocks are variable, but mostly granitoids or even gabbros and so on and so forth, intrusives. Here, you have an important component of the volcanosedimentary unit as host to the mineralization. I'm going to stick to Salobo. But before doing that, again, this is just a general sort of alteration patterns that you can see in the northern sector of Carajás. Again, sodic calcic alteration, which tends to be of regional extent. And then as you go towards the mineralizing sites, silicification may be common, but then something which is quite common in these deposits is this iron-rich alteration represented by grunerite, which is an iron-rich amphibole, almandine, tourmaline, and magnetite, which may then evolve to a potassic alteration with biotite in this case. And this is the alteration that is going to involve the copper gold mineralization, particularly breccias or disseminated and so on and so forth. For other deposits, this alteration evolves to chloride carbonate and maybe the host of mineralization as well. This is the example I want to give you of these deposits. The Salobo host rocks, gneisses. These gneisses are 2.75 gigayears. So as you go into more deformed zones or within this shear zone here called cinzento, the gneiss becomes gradually richer in amphibole. It becomes an amphibole-rich rock. And as you go towards the mineralizing zones, you have the iron-rich alteration with grunerite and almandine, which is then replaced by biotite. In this case, close to or associated with the mineralized zones. Here you have some shots of the rocks. This is the gneiss. And then when the gneiss turns into an amphibole-rich rock with grunerite, actinolite, and then closer to the mineralized zones, grunerite and garnet, which is then gradually replaced by biotite, and magnetite starts coming in, forming magnetite-rich bodies here. And this iron-rich alteration is accompanied by tourmaline as well. Then if we go to the Paleoproterozoic systems, Iosage systems, Paleoproterozoic, I mean 2.0, 1.88, mainly 1.88 so far. There are some examples. And in this case, in terms of alteration, the sodicalcic and the calcic ion alteration are poorly developed, which is different in the Newarkian. However, the potassic ion alteration is dominant in these deposits. It may contain ore, or this alteration may evolve to a lower temperature hydrolytic type alteration with chloride, sericite, a lot of quartz and carbonate, and breccias and veins and that contain the mineralization. I'm going to give you one example, which is the Sossego. Remember the Sossego here? I was talking about the Sequeirinho. Sossego is Paleoproterozoic. And this is the sequence of alteration that you have. This is a granite, in this case, a 2.75 granite. You do see some calcic alteration, but it's very local. It's not widespread. This is gradually replaced by a potassic alteration with potassic feldspar, and later everything replaced by chlorite. And here you have ore. The ore here is a breccia. And note that this breccia is very different from the Newarkian ones. This is a Krakow breccia. The matrix here is carbonate and quartz and chalcopyrite, apatite, and so on and so forth, more brittle stuff. And this is the breccia, and all the dark rims that you have here is magnetite. And this is the mineralization dominated by chalcopyrite and a series of other minerals and subordinate phases as well. Just to make sure that you guys have seen this, this is Paleoproterozoic. So this is the dating that we've done in monazite for these Sossego deposits, confirming that it's Paleoproterozoic. I'm getting to the end, and I'm going to just touch the fluid regimes associated with these systems in Carajás. And very much like the other systems worldwide, what you see, it's highly saline fluids that coexist with lower saline fluids with CO2 or without CO2. If we put that into numbers, in terms of relating salinity with temperature of the inclusions, the pattern is the same. Higher salinity, higher temperature, merging into lower salinity, lower temperature. So most probably suggesting a mixing or the involvement of different types of fluids and suggesting mixing as well, which might be very good for copper deposition. In terms of sulfur sources, this is the bar that represents the magmatic sulfur, and you can note that, well, for most of the deposit there is a magmatic component for this sulfur, but in many cases, if not in all of the cases, it shows that sulfur has not one single source. There are several values here that are much heavier than expected for the magmatic source. So you may have several sources of sulfur for these systems in Carajás. Something that I'd like to pinpoint, which is quite interesting in Carajás, it's the multiple ore forming events that you can see in one single deposit, when you describe one single deposit. And I'm going to give you just one example. One example comes from the Igarapé Bahia in the northern part of the belt. It's Neoarchean, 2.56. Geology is like this. Mafic volcanics in the base, together with some felsic volcanics. On the top, a siliciclastic unit with greywackies and conglomerates, so on and so forth. And what you see in this sedimentary sequence are chalcopyrite nodules immersed in peelites, for instance, or chalcopyrite nodules that are concentrated along the lamination of these sequence. So question here is, am I dealing with an early copper mineralization? Am I dealing here with the first whiffs of copper in the Carajás Basin, in something like that? A work which was done by a colleague of mine, Gustavo, and he's published recently. So some fumaroles here during the evolution of the volcanosedimentary sequence, and already bringing in copper into the system, making this volcanosedimentary sequence part of the fertility of this belt. But if you continue describing these rocks, what you're going to see is deformation. And as you see deformation, shearing, well, there goes magnetite coming in. And then the IOCG system, which is 2.56. And then this mineralized, this is ore, this is overprinted by a later set of veins with quartz and carbonate with chalcopyrite. It's not vein, it's not ore, but it may be paleoproterozoic. So several events that are overprinted in one single deposit. Concluding remarks, because I've gone over 20 minutes. First of all, I think that I have made a point that in terms of IOCG systems in Carajás, we're dealing with multiple ore forming hydrothermal events that has taken place in the Neoarchean 2.7 and 2.56, as well as in the Paleoproterozoic, particularly here in 1.87. So here at 2.7, here at 2.56, and here at 1.88. Particularly in this case here, in the Neoarchean copper systems of this age, the age of these systems have or show no overlap in time so far with important bimodal magmatism in Carajás. They are all older than 2.75. On the other hand, the 2.56 deposits in the northern sector, well, they do have a close temporal relationship with the 2.56 magmatism, which is poorly constrained in the area. It doesn't mean that it's not there, but it's very poorly constrained. And on the other hand, the Paleoproterozoic, this is wrong here, but anyway, Paleoproterozoic copper system here has a clear temporal link with the alkaline A-type Paleoproterozoic granite magmatism in the area. But then the question is, does this magmatism is actually acting as a source for fluids? Is giving off fluids as well? What is it? What is the role this magmatism. Putting all together and just to simplify things, we think that the Newarkian systems in Carajás are deeper, obviously are structurally controlled, but they tend to be deeper when compared to the Paleoproterozoic examples, such as Sossego that I showed you. There are some others, right? In this case, here, the deformation has a very strong brittle component in terms of the Paleoproterozoic systems. Fluid regimes in both cases seem to be quite, similar. You have hypersaline fluids mixing with lower salinity, lower temperature fluids, possibly as a mixing system that may be an important trigger to copper mineralization. These brines, based on particularly oxygen and hydrogen stable isotopes, have been interpreted as magmatic. And that would be responsible for the metal leaching within, for instance, the volcanosedimentary sequence within Carajás. However, there is the mixing process, so the involvement of other external fluids that may be meteoric if we're dealing with shallower deposits, or maybe some other types of fluids such as basinal fluids and so on and so forth. However, the importance of magmatic versus non-magmatic fluids is still debatable, although the magmatic model has become more popular. At the end of the day, whether you form an IOCG system or not at the deposit scale, among other things, is dependent upon a combination at the deposit scale of factors such as sulfur availability. We do have mineralization in Carajás that would look like an IOCG in every sense, but it has no magnetite, right? So it depends on sulfur availability and the redox conditions during fluid-rock interaction or fluid-fluid interaction. Well, Jesus, this is what I had to say to you. Thank you. Well, first of all, sorry for going slightly over my time here. And I hope that this presentation may have been of some help to those that are actually watching us. Thank you very much.
Thank you very much, Roberto. I think we went a little bit over time, so we will have to keep the questions at the end. We received lots of questions for you in the chat box, so be ready at the end, the discussion time. So Hamid, if you'd like to, sorry?
If I don't go to bed, okay.
Hamid, if you would like to start your presentation. Thank you, Roberto.
Thank you, Johan. Well, my contribution today is going to be give you an overview of mineralization in the Great Bear Magmatic Zone, the Northwest Territories, Canada. I would like to acknowledge those who have helped with our work over the years, but we'll get right into it. The Great Bear Magmatic Zone is actually a short-lived extensional relapse within the Calderian orogeny, with the typical Andean Cordilleran type orogeny. The zone is exposed here on the northwest corner of the Canadian Shield, and it's exposed over about 450 kilometers. The mineralization, or the IOCG systems, they are associated with this 1.873 to 1.865 billion-year-old plutonism and volcanism, and it's left behind a series of remnant volcanic belts, which are shown here in this purple color. They're actually former volcanic systems. There were about 10 former mines in the belt, but they were all epithermal veins that occur within and are part of very large IOCG systems. So I'm going to take you on a tour of the belt, and we'll start in the south, and then we'll Sudayan and Nico, and then we'll end up in the Echo Bay district on the eastern shores of Great Bear Lake. So here we are in the southern Great Bear, Nico, where the Nico and Sudayan deposits are located. What's important here is the underlying Marion River granitic batholith, as shown in pink. And it's its own overlying volcanic pile, which are these rhyodacite volcanics, known as the Faber group volcanic, known in yellow. The batholith includes a older sedimentary sequence shown in gray, and it's the older sedimentary sequence that actually hosts the Nico, or the bulk of the Nico gold, cobalt, bismuth, copper IOCG deposit. The geotectonic setting for Nico something like this. It's a Marion River granitic batholith, and it feeding a series of parallel on echelon bimodal porphyry-like dikes. And this is actually a parallel dike swarm. And right away, when you see that, you should start thinking extensional tectonics. Feeds the overlying ignimbrite volcanic rocks. And it cuts through this siltstone wacky sequence, which actually hosts the ores. The lower part of the siltstone wacky, it's actually hornfels and indurated. It's contact metamorphism from the Pluton, but the upper part seems to remain permeable and got mineralized. But the mineralization is actually capped by a felsite that is a K-feldspar altered basal part of the ignimbrite sequence. So the mineralization and alteration, forms and ponds just underneath the volcanic rocks and forms this magnetite ironstone, which is basically a potassium feldspar biotypable magnetite tourmaline alteration with stratiform mineralized layers of sulfur arsenides superimposed on that, hosting the gold, cobalt, bismuth, copper mineralization. And that ironstone grades peripherally into biotite hematite alteration that grades into hematite, and then more distally into sericite. So we'll take you on a tour and show you some of the rocks in the area. So the deeper part system has all these albite alterations of the metasediments all the way up to albitites. And in places, the albites are cut by magnetite and amphibole alterations, as shown in the upper left photographed here. The system is kept by this potassic K-feldspar alteration of the lower basal part of the ignimbrite sequence, and it forms this in places this massive felsite, very impermeable. So very little of the mineralization got up into the overlying volcanics, and it's pretty much confined to the zone beneath this. Well, here potassic feldspar, hematite altered rhyodacite cap rock, and immediately under that you have the Nico ores, which is this amphibole biotite altered metasediments with the sulfarsenide ores. And the ores, they look like what you see here. And it's basically, the ore itself are these sulfarsenides, which are primarily cobalt and arsenopyrite, with cobaltite, native bismuth, bismuthinite, native gold, and gold silver tellurium alloys, which host the mineralization in the altered metasediments. Okay, so moving 22 kilometers north of Nico, we have the Sudayan deposit, which again is associated with the Marion River batholith, and overlying the batholite is this large rhyodacite ignimbrite sequence. Has a lot regionally, there's quite a bit of potassic alteration, but the Sudayan deposit itself is located right at the intersection of these major crustal lineament, the Diane Lake Fault Zone, which cuts right across the Great Bear Magmatic Zone, and it occurs where it intersects a north trending fault zone here. And we have this nice breccia complex, which the next slide will show you a cross section right through that. It's very well posed at surface and drilled, so we have a pretty good idea what it looks like. But here at Sudayan, we're grading from the Marion River batholith, which progresses into this porphyry stock, which is pushing its way up through rhyodacite ignimbrite, and actually forms both a true structural, as well as a topographic domal feature. And at the apex of the porphyry stock is this hydrothermal diatom breccia with the copper, gold, silver mineralization. in terms of alteration in the system, distally, it's Sarasit grades into potassium feldspar and then hematite with K feldspar, and then you get into the magnetite hematite hosted breccias in the central part. This entire system from magma to surface, and it does appear that it actually breached surface. So we have this kind of fallback looking breccia here, paleoregolith at this height. This magma to surface, it takes place over about 300 vertical meters. So at depth, it's barren magnet-hosted breccias with pyrite, which grades into magnetite-hosted breccias with chalcopyrite, then magnetite hematite in the central part, and then the upper part is purely hematite-hosted breccias with bornite, chalcocite, and cobalt mineralization. Okay, so this is just the host rhyodacite nimbrites. That's extremely well preserved, welded tuff. And like these are 1.85 billion year old welded tuffs. And the basal part of every nimbrite sequence is a fragmental tuff. And here you can see these pumice, which are starting to become flattened and incipiently potassic altered. The uppermost part of the system is the only part of the system where we have a uranium and pitchblende veining. So you see the black is actually pitchblende veining, and the yellow and orange, that's the uranophanes from weathering. Blue is a bit of mineralization, but that only occurs in the most distal, most oxidized hematitic breccias in the upper part of the system. Here we're standing actually on the Sudan Dome looking across Diane Lake at quartz feldspar porphyries in the distance, and in behind that hill is actually the Marion River batholith. The central part of the deposit is typical classic IOCG type hydrothermal breccias. The fragments are potassic or dignimbrite, and the dark matrix is magnetite, hematite, chlorite, epidote, garnet, and fluorite with the chalcopyrite mineralization. As we mentioned, it grade downwards into magnetite only hosted breccias and upward into hematite only hosted breccias. The deeper part of the magnetite, as we get to the upper apex of these porphyry stock fingers off the porphyry stalks, the upper part of the porphyry is potassic altered. So it's actually altering itself, and right to the point of becoming almost a felsite. And you can, and that upper part of the porphyry stalk, it actually grades downwards into deeper parts of the porphyry into this very albite rich part of the porphyry system. Okay, so we're going to head to the north now to Echo Bay. This district, we're on the east shores of Great Bear Lake, and there we're into an andesitic stratovolcano complex. This central part here, which is about 5 kilometers across, is known as the Collapse Cauldron, or the Echo Bay Collapse Cauldron. And a volcanic center. In fact, it's not the volcanic center, but it is one of a whole series of volcanic centers along what actually forms a linear belt. In green are all the acidic rocks, but what's feeding that are these diuritic and monzodiuritic plutons. These the plutons themselves at depth, it's diorite, and the only reason they're called monzodiorite in places is because the upper parts of the diorite, it's actually potassically altering itself, so it becomes and ends up looking like a diorite. And these are actually a series of sheeted plutons that extend for many 10 kilometers, and there's at least 3 major ones in here. So when you see that sheeted plutons, again, there's another very good evidence that we're dealing with a rift type environment. Most important mines or past mines in the area were the El Dorado and Echo Bay mines, and in particular El Dorado, which was the founding enterprise of Atomic Energy Canada. So here we're looking across the northern part of Echo Bay towards Port Radium in the distance to get an idea what the geology looks like. And this is actually a diabase sill running in all the way through here, and there are several of them, which again, another clue that we're in a rift-like environment. So next photograph is the peninsula there, Port Radium, the former site of the El Dorado mine, which is where they mined epithermal quartz carbonate hematite veins with uranium, copper, silver, cobalt, nickel sulfides, and arsenides that are associated with overprinting extensive magnetite, actinolite, apatite alteration, potassic, phyllic, and also propylitic alteration zones. So most of the peninsula that's using here is actually very intense magnetite, actinolite, apatite rock, and it's actually vanadium magnetite in there, which is a bit unusual. So take a look at this bay in here just for orientation for the next slide. So that's that same bay that I just pointed out to give you an idea of scale and orientation. And this is the geology of the El Dorado Echo Bay mine areas. Again, the diorite intrusions coming through, it's faulted off and then it continues as porphyritic diorite and monzodiorite. So these diorites here are actually the higher level exposures of the same diorite that you see here, where they're just potassic altered. So in the deeper levels of the system, where it's just diorite, you can see it's associated with magnetite actinolite alteration. So this whole section's magnetite actinolite altered. And the upper parts, where it's diorite, which is potassic altered diorite, all the rocks are potassic altered, like regionally right through and all the way down through here with little, all in red are the little, not like actually fairly large pockets of very intense phyllic alteration, which grades at depth into the potassic alteration. The next slide puts some tectonic perspective on what you're seeing there. And what it is, in fact, the whole system is hosted along another one of these northeast trending crustal scale faults that cuts right across the entire Great Bear magmatic zone, where it intersects another cross-cutting fault, the El Dorado fault zone, which is responsible for the formation of this pull-apart basin along what would otherwise be a strike-slip fault zone. And along that pull-apart basin, these monzodiorite intrusions come up and they've caused the alteration and the mineralization. The epithermal veins of the old El Dorado mine are shown here in red. And if you actually wanted to find the extension of those down in this lower Echo Bay mine block, you'd actually have to look about 300 or 400 meters deep. And the reason is that this is a relatively a down-thrown block compared to the El Dorado block, which is an up-thrown block. And we know that because of the alteration nature of the intrusions, which indicates deep level exposure. And over here, the exposure is only the higher level parts of the. So further to the southeast along Echo Bay, which itself is about 20 kilometers long, we have what we call the contact belt, which is an example of mapping in the whole Echo Bay district. We've actually mapped in detail the entire 400 square kilometers of exposed volcanic rocks. And in that entire 400 square kilometers, I've never seen a hydrothermally unaltered volcanic rock. And this is just an example of what you see when you map there. The least altered andesites are propylitic, and it's a very intense epidote chlorite carbonate sericite alteration. The next most intense alteration is actually phyllic zones, which is classic quartz cerous pyrite, shown in yellow on the right side. And this phyllic alteration actually grades at depth into potassic alteration, that is potassium fells. And you can see how widespread that is. It's this beige area. This is all K-feldspar, widespread K-feldspar alteration. Now here's the outline of the monzodiorite pluton, or part of the monzodiorite pluton, and you can see that the alteration doesn't respect geological boundaries. But the source of all this alteration is in fact monzodiorite, and it's altering itself as well. The potassic alteration, it grades into large areas of hematitic alteration, and it goes from hematite dusting of the andesites all the way through to massive replacement and hematite bodies as shown here, and at depth under the K2 zone. Locally, there's tourmaline gets into the system, and in deeper levels, actinolite shows up, and then it leads into deeper areas still of actinolite magnetite, and then actinolite magnetite apatite. So typical IOA type alteration, very intense in places, shown in the gray and black, and the gray down here. And underlying parts of that is albitic alteration and massive albites. So we'll take a look at some of the rocks in this area, and then at the K2 deposit, which is over here. Example of some of the massive albitites that show up in the area, and these ones happen to be cut by actinolite veins. But when you see this, I mean, a good question to ask yourself is, as this is all pure albite, where did all the iron, potassium, calcium, magnesium, volatiles, and other metals go? Well, they went somewhere, and hopefully we'll answer that question. Albitic zones grade into magnetite actinolite apatite alteration. This is example, like you can see hundreds of meters of this at surface. The dark is magnetite actinolite apatite. The pinky is albite and case spar. In drill ore, polished drill core, this is what it looks like. This beautiful silvery magnetite with the dark areas are actinolite with apatite. And in some areas, the andesite is actually recrystallized to this pegmatoidal rock that you see here. Again, you get hundreds of meters of this in places. It's magnetite actinolite apatite is the dark material, and the large feldspar crystals are albite with feldspar rims on them. And it is very unusual, but it appears to be like a pressure cooker type recrystallization of the andesites. So from that magnetite actinolite apatite, if we move a little bit to the east, we get into large areas where it's hematitic altered, and that hematite grades into massive hematite replacement bodies. So here's the host andesitic, porphyritic andesite with a dusting of hematite, and that literally grades into this massive hematite replacement bodies. And then if we go from the hematite and the potassic and hematite altered rocks to a structurally higher level, we get into these phylic gaussins. And these phylic gaussins, filtration that you see here, it's very, very intense. And it just grades at depth into potassic, which means case bar alteration. And that's actually a silver prospect. So on the north end of that particular belt is the K2 deposit, and at surface, it's a phyllic potassic gossan with tourmaline and tourmaline breccias showing up, and it hosts, again, sulfarsenide mineralization with copper, cobalt, gold, and silver in it. As you go at depth in this system, you begin to pick up typical hydrothermal type IOCG, like looking like this. And then about 200 meters vertical depth, you actually start going through massive hematite replacement bodies. And then as you go at further depth, you get 250, 300 meters and deeper, you get into increasing dominance of magnetite actinolite alterations. So it's just an example of some of the tourmaline crackle breccias at K2 with the copper, gold, cobalt, silver mineralization. Here it's hematite and K feldspiration of the andesite with chloritic, and the black is all tourmaline, and the white is the sulfarsenide mineralization. Here's an example where it's just quartz tourmaline breccia. Okay, this is a slide that shows Gossan Island in the middle of Echo Bay. And what we're looking here is one of these monzodiorite intrusions, and on either side you have one of these phyllic potassic alterations. At the lower levels, we start to see a bit of magnetite actinolite veins showing. But as we go down the belt, we come into the K2 zone, where it's at surface, it's phyllic potassic tourmaline, as we mentioned, depth hematite, and deeper down magnetite actinolite. But down the belt, 5 kilometers or so, we're into big, large hematitic alteration zone, and about 7 or 8 kilometers down the belt is the massive magnetite actinolite apatite zones that we showed you earlier. And then if you go northeast from the magnetite actinolite, we actually come into higher levels of the system, and we go through the massive hematite I showed you, and then into that phyllic zone that I showed you previously. So what you see at surface here is actually just nothing more than different erosional exposure levels of similar systems. So depth of formation and exposure level actually controls what we see. This feature here is interesting. It's not a fold, it's actually it's a collapse structure. And the major mineralization that we know of so far in the Great Bear is actually associated with either collapse or domal structures. Collapse structures, Nyko sits within its own collapse structure. Sudayan is a domal structure like this, and so it goes throughout the. Okay, and kind of summarizing everything that we see in the Great Bear Magmatic Zone, we can kind of forget the right porphyry side and just the magmatic hydrothermal IOCG side of this. This kind of summarizes what we're seeing. It's the batholith at depth, plutons, and then subvolcanic plutons, and then stocks arising and dikes arising from that, with sodic, or this what we sometimes refer to as sodic calcic alteration and the albite sodic alteration grades into potassic, and K feldspar alteration grades into ceracitic and propylitic alterations, and propylitic alterations at depth, with a bit of phyllic-like effects in the most distal parts of the system. And with iron oxide apatite type systems at depth, magnetite hosted IOCG type mineralization also in the deeper to the system, and the more distal, more oxidized, cooler parts becomes hematite hosted IOCG like systems. And then the epithermal parts of the system, in the upper parts of the system. So all of El Dorado and so many other things in the Great Bear would occur in these very high level parts of the system. Now, I can say without any doubt in my mind that if this magmatic hydrothermal event took place 250 million years ago, or any time during the Phaerozoic, you would have had a classic porphyry epithermal type set of systems throughout the Great Bear. So with that, I'll just give you my final summary observations, that the IOCG deposits in the Great Bear, they're associated with felsic to intermediate stratovolcano complexes with a broad continuum of magmatic hydrothermal mineralization types, which, if you know what you're dealing with, as the case here, it actually provides a great context for robust exploration. We have coalescing magmatic hydrothermal systems that occur on the scale of volcanic complexes and linear volcanic belts. The most diagnostic IOCG core alteration and throughout the belt is alkali iron, that is sodium, potassium, iron. Intermediate to distal alterations include iron, calcium, potassium, boron, carbonate, hydrolytic, and silica, there's quartz. The alteration zoning is always progressing from high temperature reduced core facies to distal lower temperature and more oxidized facies. And what we see at surface is controlled by the exposure and formation level and distance to intrusion. And finally, in the Great Bear anyways, the geotectonic setting and architecture of these magmatic hydrothermal IOCG systems have a lot of similarities to porphyry copper systems, but also some very important differences. And I'll conclude with that. So thank you very much.
Thank you very much, Hamid. I think also for time constraints, we will have to move further. And we'll keep questions towards the end. So, Christiana, would you like to start your PowerPoint? And after Christiana talk, maybe we can have a 10 minutes break in case people are getting tired. So,
is it this one? This
Christiana,
one.
please go ahead.
Yeah. Okay, thank you. Hello, everybody. Ivan, thank you very much for giving me the opportunity to talk to you about iron oxide deposits from IOCG system in the Olympic Dam district, South Australia. Now from this mega scale, a very interesting talk we heard this morning. We are moving to very detailed mineralogical and down to the atom scale. I hope you will enjoy it. Anyway, so why iron oxides in IOCG systems? Well, in South Australia, we have an Olympic copper gold province, 600 meters on the western side of the Gawler Craton. It is attributed to the emplacement of the Gawler large igneous province at about 1.6 billion years with Mesoproterozoic plutons, Hiltabasite in particular. We knew that back in 2014 from a lot of field evidence and dating. But what we didn't know is that actually we can have hematite that look just like zircon. What we know about this hematite in IOCG systems from Olympic Dam in this case, that actually it is a truly hydrothermal mineral. So we set out to understand whether we could use the iron oxides themselves to fingerprint the onset of biology systems in South Australia. So we did have a project running for the last 5 years. We call it the FOX project, and oxide mineralogy, geochemistry, and geochronology. We have had 4 PhD students with 4 main items, themes: mineralogy, geochemistry, biology, particularly in the Olympic Kapa-Gold province, but also BIFs in the Middleburg Ranges, Max and William. And then we did have a module of geochronology of iron oxides, Liam. And then we had a component of multivariate statistical analysis carried out by Maria. So Olympic Dam district itself is somewhere here. So it's one of the best endowed part of the entire belt in South Australia. And it has several prospects, and the big deposit, the superclass deposit, a 10 billion ton deposit at Olympic Dam, but also these prospects on the southern part, Acropolis, Urdawel, and Island Dam. And as any cratonic area, of course, we are dealing with some older rocks, Archean, and then we have different magmatic suites, Donington, magmatic suite at 1.25. And then we do have some volcano-sedimentary sequences, Wallaroo Group, and then we do have the Hilltapa intrusive suites with volcanics and also granitoids. This outline here also vaguely corresponds with what it was considered to be the big magmatic batholith underneath called the Burgwan batholith. So our approach was to look at this, to show you today, my approach was to show you today these 4 localities, these 4 IOCG systems that differ in terms of the local setting, and which was studied at various scales of observation. In terms of the methodology, it's important to stress that we did have quite a very heavy analytical package, micron scale characterization, petrography, and geochemistry using obviously the optical microscopy, but also scanning electron microscopy, electron microscope analysis, and laser ablation, inductive coupled mass spectrometry, combined with geochronology using different standards, the zircon standard, but then newly introduced methods such as mixed uranium lead solution by Liam, and also developing a synthetic hematite standard, and combined with ID teams, high precision ID teams of that hematite, and also shrimp methods. We had a very heavy component of nanoscale studies, which was targeting to understand incorporation in, removal from the crystal structure of the iron oxides, as well as inclusions present at the nanoscale in the iron oxides. We used in situ cut slices by focus ion beam on a polished block, on the surface of a polished block for sample preparation. And we used a method called high angle annular dark field scanning transmission electron microscopy imaging that shows us atoms as they show, as they are, and with mapping on a state-of-the-art instrument, Titan Themis, with a very talented operator, Ashley Slattery, at Adelaide Microscopy. Obviously, we have several ways of processing the data, and we did have a very important component of multivariate statistical analysis with principal component analysis, engaging with hierarchical element loading, scaling scores, as well as non-supervised algorithms such as random forest classification and computer codes written by Maria using the R software, as well as 3D deposit modeling and distribution patterns using the LeapFrog software. All right, with that in mind, let's have a look at our spectrum of deposits. So Olympic Dam obviously is an example of a deposit which is hosted within a granite, Roxby Dam granite at 1.6 billion years. And the deposit itself is outlined here by these anomalies that represent the principal component. So the trace elements associated with the ore bodies. There are 3 sections from through the deposits, and those are overlapping with the iron metasomates, the iron more than 28%, all within the breccia developed on behalf of the Roxby Dam granite. In contrast, we have Warda Well in the south, which we consider to be structurally controlled, because here the host lithologies are actually the older granite, Donington 1.85, and the mineralization, you see here the anomalies of copper are elongated along a set of dolerite dikes, which are older pre-mineralization and placed either during the Donington emplacement or a bit later at 1.75 billion years. And then we have the example of Acropolis, a prospect, an IOCG prospect, which is hosted in volcanics, ferrous volcanics. And then we have the example of Island Dam, which is hosted within Donington, but it's basically placed along a fault between siliciclastic sediment of Wallaroo Group and the Donington. So it's hosted within skarn, actinolite and phlogopite skarn. So if we have a glance at Wirda Well, again, this was the model from Hayward and Skiro, saying from the cratonic reconstruction that we are dealing with terrain bounding first order faults. Here is the Kiltapa Suite 1.6. This is the Donington host. This is the volcanic GRV 1.6. And we have a southern part of the Wirda Well, hematite dominant, and a northern part, which is Wirda Well North, which is magnetite dominant. So our area of interest is throughout the drill holes, 46 drill holes that have been processed using implicit modeling and leapfrog. And these are the way the dikes are looking, parallel to those terrain bounding faults. And in 3D, we do see how those dikes relates to the deposit itself, north and south. Varied lithologies, shear zones, Donington granite shears, altered iron oxide patchy or like veins, and here are the mafic dikes. You can have a sort of a look how it looks, very complicated. However, through the PC analysis, principal component analysis, we could depict, I don't know if you see this on the side here, but we could depict 5 clusters, lithogeochemical clusters by K-mean clustering. And in particular, we could depict the magnetite and the hematite signature, which relates to Wirda Well North and Wirda Well South. And moreover, we could actually use signatures of the magnetite and the hematite cluster. Magnetite is this transitional element index there, vanadium, nickel, cobalt, titanium, and hematite bringing in the uranium, molybdenum, tin, tungsten, and also chalcophile elements, arsenic, silver, bismuth. And you can see how Acropolis and Olympic Dam are different to one another. So Acropolis is less evolved than Olympic Dam. Whereas in Wirda Well, the hematite part, Wirda Well South, partially overlap with the Olympic Dam cluster. So the statistical analysis give us a way of comparing the various deposits and prospects throughout the Olympic Dam province. At the heart of it is that we are dealing with this granitophile group elements, uranium, moly, tin, tungsten, which seems to be very typical of what we have in the Olympic Dam district. If we move on, this is an example of this fault control prospect at Island Dam. You can see anomalies depicted here, the same, apart from iron and copper, we do have molybdenum, tungsten, and uranium, very well depicted. And we do have hematite that actually was dated. And it returns, the skarn hematite, it returns the same age, 1.6 billion years, as the other deposit throughout the Olympic province. So this is dating of the hematite itself. So moving on, actually we did look at hematite from Wirda Well and also uranium-bearing hematite from Acropolis. And we obtained similar kind of ages, 1.6 billion years. And you can see here the dating. Can you see this, Iwan? My screen seems to be to the right. I can't really show you very well. Is that true? Okay, I'm moving on. So actually, Now looking at the Olympic Dam itself, you see here a geological sketch at 350 RL. And what is important, we have the Roxby Down granite outside, the least altered, although there is no such thing as unaltered granite at Olympic Dam. And then we have an outer shell in which we have the granite with various appearances and brecciation and sort of different, nodules of iron oxides, but also veins, rich veins with iron oxides on the eastern side, where we looked at in more detail. And here we do have some intervals, like 10 meter, 20 meter intervals with massive magnetite. Important for what we see in the outer shell of the ore body at Olympic Dam, which is pointed here in green, is that we are dealing with a lot of interconversion between magnetite and hematite. Although it's magnetite dominant, it is at all times the two iron oxides together. The fact that the magnetite is not free of inclusion is actually oscillatory zone with respect to inclusion. Silica rich is silicium magnetite up to several 8% CO2. And in the nodules, like from this one here, we again see a lot of integrals between one or the other iron oxides, but also siderite. At all times, we have very fine mottled patterns with chalcopyrite and pyrite with sulfides between the two iron oxides. So moving on, some magnetite geochemistry from this outer shell. You would see here that importantly, we still have uranium, we have rare earths, high field strength elements from the different location. Based upon the relationship we are seeing, we can model in those kind of geochemical diagram like shown here that actually have a transition from iron titanium oxides, magmatic in the granite to early hydrothermal stage, during which ilmenite breakdown leads to formation of titanium oxides, rutile, and then to titanium-rich hematite, plus high field strength elements rich hematite. We do have direct overprint of the magmatic magnetite by silicium magnetite, and that corresponds to those conditions there, just when both potassium feldspar and sericites are stable. And the next stage is where the sericite takes over, and in that case, siderite replaces magnetite. We do see also skeletal growth between siderite and magnetite. Based on all of those, we came across with the model of the formation of the emplacement of the RDG, part of the bigger Bourgoin batholith, with this deeper zone of mingling with mafic and felsic magma, and moving out into the upper crust. However, what we understood is that actually the outer shell is formed at a deeper level, 6 to 8 kilometers, and then we have a cupola collapse, which will form the ore body in the middle of that RDG emplacement, RDG granite, and it's at that stage that actually the IOCG, the copper gold mineralization, it's formed somewhere upper in the crust at 2 to 3 kilometers. Now, of the magnetite that is around the ore body at Olympic Dam, we do actually have from the massive magnetite intervals, a magnetite that is different in age. We've been able to date it by the two methods, either using zircon as reference material or the mixed uranium-lead solution, which is very good overlap between the two ages. It is rich in rare earths, it is rich in uranium, and this magnetite returned us an age at about 1.76, a time where we have a coincidence between sedimentation and iron-rich intervals and also emplacement of Pluto's granites that for sure would have contributed to the fact to the enrichment in uranium and rare earths in that magnetite in the outer shell at Olympic Dam. So the uranium concentration we are seeing in some of South Australian IOCG systems, and which represent major global anomalies, could be a combination of the fortuitous geological circumstances. So cite Gautier with his ideas about formation of ore deposits. So moving on, if we now look at the ore body at Olympic Dam, which is within this outline here, which coincides with the outline of iron over 5 weight percent, and that's the copper resource line. The southeastern lobe is actually quite deep, goes to more than it's open at depth of 2 kilometers. And we have taken a dual approach looking at the mineralogy of the iron oxides. Max did that, and also using the same hematite to actually develop the geochronology and try to understand the magmatic hydrothermal window using high precision dating of hematite and zircon in the case of Olympic Dam. So hematite from Olympic Dam looks like this. It is a variation of the theme of oscillatory zoning with respect to tungsten, uranium, tin, moly, and obviously the radiogenic lead. And it is multiple sets of twins. It forms aggregates. It is a variation of replacement and again more oscillatory zoning. And sometimes for new minerals and like rare earth minerals are sealing those recrystallization of the hematite patterns. So could this be actually an archetype for IOCG deposits that have hematite in them? Well, we started to look around. I can just give you, we have an example elsewhere. So we look at some of the hematite in the Atacama Fault zone, and as you can see here, that hematite is still and tungsten rich, and it is oscillatory zone. And it has very little uranium, actually a few ppm uranium. Nonetheless, with the new standard, we could date that hematite, meaning that we obtain an age which is slightly younger than the pre-existing age, which was for the magnetite apatite deposit along the Atacama Fault. So that gives us hope that actually this type of hematite, with what we call granitophile trace element signature, uranium, tungsten, tin, and moly, might be something that would be typical, an archetype for all the beginning, the first form hematite in many IOCG deposits worldwide. All right, so this magmatic hydrothermal window, as I said, we have engaged with very high precision IDTMs uranium dating of hematite. These are the best dates we obtain, and zircon with the chemical abrasion treatment, pre-treatment before dating, and the data altogether is here. And we back up the previous schematic of the Olympic Dam deposit. We have this lithospheric model with a zone of partial melting in the upper mantle with a lot of mafic and ferstic magmatis forming the batholith here. And then in the case of the Olympic Dam district, magma reservoirs, first start of the crystallization at 6 to 8 kilometers, and then uplift and collapse, cupola collapse. It is not a marked diatreme as it was previously considered, in our opinion. It's actually formed at some depth. And this was constrained within 2 million years between zircon and the earliest magnetite. And we can say that this kind of work, we know that we can date with quite high precision, up to 0.5 uncertainty, lead ages, Mesoproterozoic hematite. So here it is. We have tested, and we have now we are now confident that hematite, it is a mineral geochronometer. We have assessed it by multiple techniques, rim, additives, mapping with laser ablation to show the different isotopes, domains that are closed and domains that are open, not so good. Our technique for additive was to actually microsample using laser ablation trenches, then forming the aliquots for the additives. So that's very important to understand if this is the way it looks, if these are the data we get by dating. So how does it look at the nanoscale? So this uranium-rich oscillatory zone hematite is actually quite, it doesn't have any uranium or lead inclusions. What it has when it is very, which is higher than 2 to 3% uranium-02, it starts to develop needles or lamella, nanometer-wide lamella, or just atom-wide lamella of magnetite. So there is a transition from the rhombohedral hematite into the magnetite, controlled by faults and defects, as you can see here at the atomic scale, and in the very high bonding with uranium, we do have the shear displacement structures and faults, we think that this kind of formation of magnetite at the nanoscale occurs as we reach the upper uranium solubility limit in hematite. So this finding is very important in that saying that uranium is not actually as inclusions, but is closing, it is part of the hematite crystal structure. But nonetheless, Olympic Dam, it's a breccia IOCG system and has a lot of bad hematites. So there are a lot of textures indicatives that actually the grains have been replaced. At Olympic Dam, typical of most of the mineral replacement is a pseudomorphic replacement coupling dissolution with their precipitation rates. That means we can transmit primary signatures into the newly formed product, which could be just the same mineral, but just with slight changes in the signatures. A very good way to open the crystal to that free mineral interaction are twins, plenty of twins in hematite. Here are twins which we can fingerprint at the nanoscale as being rich in aluminum, silica, and potassium. So serialization started, and you can see the scale there. More about that during those overprinting episode, so the morphing replacement of hematite, we obtain unusual oscillatory zoning with respect to copper arsenic and otherwise granitophile rich hematite. So it is twinned, the hematite, and along those twins we see occurrence of copper and arsenic, as well as nanoparticles of copper arsenic also with during the silicide formation. And also we can see this kind of inclusions along trails that looks like preserved fluid inclusions. So this is a schematic showing how we think about the formation of the twins, starting by one set and bringing the other set during the percolation of silica, aluminum, potassium bearing fluids. And then as the fluid takes off and becomes more, the interaction, the percolation is more intense. With throttling, we can develop the swelling structures and form the fluid inclusions. And in some of those fluid inclusions, we will have native copper nanoparticles or copper arsenic nanoparticles. So I like to stress the role of twins in trace element remobilization. With this study case of one of the bad hematite. Another bad hematite, which is even closer to our subject, is that interaction between hematite and incoming fluids can actually disturb the uranium-lead ratio. As you can see here, we have a case of a hematite in which we see preferential removal of tungsten relative to tin. and somewhat more patchy uranium and lead, which this type of hematite is actually very tungsten rich, has 2 to 3% tungsten oxide. The uranium is just in thousands of ppm. So this grain has been actually sampled for ID teams with no luck in terms, they didn't obtain any age model, but also has been dated by laser ablation when we got an age which is roughly 1.6 billion years, but it's not a very good age. So why is that not very good? Because the twin planes, the crystal is heavily twinned, again, 2 sets of twins. The secondary twins actually show tungsten and lead, meaning these are the twins here, image at the atom scale, and nearby those twin planes, we do have a lot of modification of the crystal structure. Not only we can fingerprint the elements that are removed or coming in from outside with the fluids, but we can see actually that we are dealing with a larger crystal structure of that hematite. We were able to constrain a twofold hematite superstructure involving oxygen vacancies that allow account for interaction between incoming fluids along these open twin planes and the host hematite that was initially rich in tungsten, tin, uranium, mori, but in this domain here, we actually lost the tungsten almost completely, whereas here we have various, proportions of removal of the tungsten from the hematite and inherently of the lead, disturbing the uranium lead systematics. If that is the case about the hematite, what about the magnetite? Magnetite, throughout all the samples we look in Olympic Dam district, actually is full of inclusions. At Olympic Dam, we have, we recognize a magmatic magnetite with spinel group minerals and ilmenite, and we do see the direct contact between magmatic magnetite and silicium magnetite, spinel ilmenite in the magmatic magnetite, and calc-silicates plus rutile inclusions in the silicium magnetite. At Olympic Dam, the alkali calcic alteration is actually through the coupled dissolution and precipitation reaction kept within the place of, at the micro scale and sometimes at the nanoscale only, unlike in the previous example we've seen this morning. So magnetite is silicium magnetite. It means that this concept about having defective magnetite, that this can here came from actually beef samples in Western Australia, and is characterized by silica enrichment along these defects, which has been modeled as being a type of vacancy order type of magmite with a lower cubic symmetries and the spinel. We do have this kind of defects at Olympic Dam. You can see them here, but also we have rounded glazed silica iron rich in Olympic Dam. Together with those silica iron rich defects in magnetite, we also have calcilicate inclusions, amphiboles, actinolite, but also epidot here we see, and we know from this high resolution imaging combined with STEM simulations that this is indeed the epidot. And similarly, in Urda well, for example, the deep magnetite in Urda well, we'll be able to identify chermokite, and we interpret that to be formed, to be inherited from pre-Hilltaba, pre-1.6 billion years LCG event during the metamorphosis at 1.75 of the Donington granite, in which is quested. Here it is. So
sorry, Christiana, do you have more slides? We are running out of time.
Yeah, all right. So this is magnetite from Urda well, and this is my last one, yeah? This is the magnetite from Acropolis, which is very much with trellis ilmenite, and we could derive 600 degrees temperatures of formation, lots of spinel inclusions, lots of other details telling us that actually we are having conservative transition from spinel to ilmenite, as well as identifying, anatiles and rutile during the cooling of the magnetite from Acropolis. And in terms of the highlights, I already took it through. It's about the geochronology, the standard, the fact that we can date both iron oxides. We have refined some of the genetic models for Olympic Dam district. And we have been able to identify the signatures of magnetite and hematite through the multivariate statistical analysis. Importantly, we believe that hematite is a common denominator that can resolve spatial temporal relationship in hematologic province, whereas magnetite is actually something that records a variety of inclusions which can discriminate among the local setting. Thank you for your attention, and here is a list of people without whom we couldn't have any of these results. And I also have at the end a list of papers I've been using for this presentation. Thank you.
Okay, thank you very much, Christiana. Because some of the people are short on time, we are not going to take a break. So let's move further to George. And George, are you ready?
Yeah, I'm ready.
Okay, George, can we keep it in 20 minutes, please?
Yeah, I'll do my best.
Okay, thanks. Go on.
So I'm not going to get too technical into the nitty gritty. I just want to go over a little bit about the work I did on the E1 group of IOCGs in Cloncurry and
George, your screen is not shared.
oh, sorry.
Yeah.
All right, can you see it now?
Yes, we can see
All
it,
right.
but it's not on
So-
the, perfect.
All right. So yeah, I'm not going to go too much into the technical here. I kind of want to I'll go through the geology, and then I want to talk about the mineral system aspect, and I might say some things that are controversial, and I hope so. I hope it can get the discussion going later on. So we've seen a lot of variety so far in IOCGs, and there's a lot of outstanding problems with how with this deposit or group of deposit models. There's not really a big consensus on the fluid sources or a general genetic model. As you can see, there are a variety of systems like Olympic Dam and Ernest Henry, Carajás, and others that are considered to be largely dominated by magmatic fluids. And then you have systems like the Wernicke breccias, which aren't really economic and are considered to be amagmatic, possibly have some sort of basinal fluid. And then deposits also in Cloncurry like Stara, Osborne, that are possibly derived from metamorphic fluids. And sorry, my cat's going to join us here. The problem also that we have is that the tectonic setting of these older IOCGs that we've heard about so far are not well constrained. And the breadth of deposit styles and observations that we have are difficult to, in my opinion, to reconcile solely with magmatic only systems or only non-magmatic models. So we basically need fluid mixing to explain the mineral assemblages we see, like in the Cloncurry and Gawler Craton IOCGs, the assemblages of barite and sulfides. Those are really hard to reconcile with a single fluid. And so just bear that in mind as I go through this. And when I mean a mineral system, I'm sure most of you are familiar with the concept, but you have your progression from at different scales in space and time of your source of your fluids and your metals, the ligands, and the transporting agents, and then your depositional gradients or your traps where the ore deposits are ultimately formed. And these can go from the large scale at the cratonic scale all the way down to the deposit or the hydrothermal system, which is here. But the entire mineral system encompasses a larger footprint than that, particularly with IOCGs, where we see this regional sodic calcic alteration that's so common. So a concept that I'd want everyone to keep in mind is that we see all this variability in between the iron oxide apatite and IOCG deposits, and perhaps this represents preservation of different parts of these large mineral systems. So my study area is in the Cloncurry district, which is the eastern fold belt of the Mount Isa Inlier in Queensland. Regionally, the rocks are Proterozoic in age. Between about 1800 MA and 1600, you have deposition of sediments and eruption of volcanics. There's a protracted deformation between roughly 1650 and 1500 that's called the Eisen orogeny, with peak metamorphism around 1600 to 1580. And between 1550 and 1500, you have intrusion of these red blobs here, the Williams-Naraku batholith, mostly A-type granites. And there are two phases of IOCG style mineralization in this district. There's the pre-igneous systems like Osborne and Star that formed somewhere roughly between 1600 and 1575, which are broadly synchronous with peak metamorphism and other deformations. And then you have the syn igneous IOCGs like Mount Elliott, Ernest Henry, E1, Monikoff, Eloise. These are all a bit younger. They're coeval with the Williams-Naraku batholith, and also with a later stage of deformation that's more brittle ductile. And the E1 group is far to the northeast here. It's about 6 kilometers from Ernest Henry, which is roughly the largest IOCG ore body in this district. You'll notice these are in white. That means they're under cover, about roughly 30 meters of younger cover. So this is represents the only exposure. And Ernest Henry's about over 200 megatons at a % copper. So it's actually fairly high grade. And zooming in, this is just an Aramag view. Ernest Henry's in this major northeast southwest trending shear zone, and the E1 group, which is a cluster of 3 small ore bodies, is over to the east here. This is a major structure, the Mount Margaret fault zone, which is correlates to up here on this regional map. And this is thought to be a northern extension, or sorry, a northern continuation of this Cloncurry structural zone, which spans the entire fold belt north to south and is a major regional structure for mineralization. And this is just what the site looks like. Again, it's buried under cover. The only topography here are the Ernest Henry waste dumps. This is what the open pit looks like after it was mining had more or less finished. And the total size of E1 is about 47 megatons at about 0.7% copper and 0.21 grams per ton gold. So it's not a particularly large ore body, but it's useful in what it tells us about these systems. So the host rocks at E1 are dominantly these intermediate volcanics. They're part of the roughly 1750 MA Mount Fort Constantine volcanic suite. They're intercalated with silicious marbles and other metavolcanics like tuffs and breccias. These are presumably the Corella marbles, which are overlap in age with the Mount Fort Constantine volcanics. And then there's a stratigraphically higher unit, carbonaceous metashale, and carbonaceous to calcareous siltstone, which host mineralization. These are also interpreted as Corella Formation sediments. Previously, but prior to my work, they were considered part of the Tool Creek volcanics, much younger, but they seem to be roughly 1750 to 1740 MA volcanics. They're intruded by the Ernest Henry Diorite Suite, which is about 1650 MA intermediate plutonic suite. And then there are these bizarre breccias that are strongly altered to chloride, hematite, albite, that are essentially barren, devoid of mineralization, and they're discordant to the to bedding. And then there's some minor dolerite dikes that could potentially be Tool Creek. We don't know. They're not. They haven't been dated. So I did some leapfrog modeling using a pretty thorough drill core database, and this is the first 3D geologic model for this system. And as you can see, the E1 group ore body, the main ore body, the largest and highest grade, is E1 North here, which is at the intersection of this antiform hinge with these northeast southwest trending shears. There's E1 East, which is kind of by itself and surrounded by this barren breccia, and then E1 South, which is hosted in a synformal structure. This is the Mount Margaret fault zone, which is possibly part of the Cloncurry fault zone system. And then you can see the outline here of the copper ore shell. So you can see what's interesting, the mineralization is essentially restricted to these thin metasedimentary horizons, the blue here, which is marble, and this brown unit, which is the siltstone. So the gray are the Mount Fort Constantine volcanics, and they're essentially unmineralized here. So the folds are probably D2 associated with peak metamorphism. That makes the dominant fabric. Then later on, you have these shear zones developing, which control the mineralization at E1 North. So you can see these little blobs here. These are shells of the copper mineralization as well as phosphorus, which was assayed, and you can see they're pretty strongly structurally controlled. In the open pit, we can see these the magnetite alteration focused into these very narrow shear zones, and these appear to be conjugate to these larger structures here. So the fold hinges and the shears are really the primary structural controls on the mineralization. And then, of course, it's offset by later structures that are post mineralization. At E1 North, so these are shells generated in Leapfrog again, and the red essentially is phosphorus, which corresponds to apatite alteration. Iron corresponds to magnetite. There's very little hematite in this deposit. It's a magnetite dominated IOCG. And what's interesting is that the magnetite and apatite form a distinct zone sort of southwest of the copper ore body, which is here. The paragenetic sequence is characterized by the regional soda-calcic alteration that is always prevalent. It's probably unrelated. It's a regional thing. The main mineralization are in the metasediments again, and they are characterized by replacement textures. So we don't really see mineralized breccias here, which is kind of unusual. You have a pre-ore stage that's magnetite, biotite, fluorine-rich biotite, K feldspar that's all barium-rich, fluorapatite, and with quartz. And then that's overprinted by the main mineralization of chalcopyrite, fluorite, barite, and carbonate. So you can see the chalcopyrite here with magnesium, iron-rich carbonate. This rock here, it's a marble that's just been entirely replaced by magnetite, barite, chalcopyrite. Some of this material might assay 20% barium, which is quite extraordinary. We dated monazites that are coeval with the chalcopyrite. The ages didn't come back very well. Monazite's notoriously difficult to date in these IOCG systems. It's quite young. It's potentially overlaps with the 1500 MA last stages of the Williams-Naraku batholith. And the alteration patterns are interesting. So these are the plan view. The red is the copper ore body, which you can see is focused in this antiform. Here you have your apatite, your magnetite. So the magnetic high actually does not overlap with the main copper ore body. And then in cross section, you can see this green represents the barite alteration, purple is fluorite, and it's much deeper in the ore body with sort of a cap of manganese-rich carbonate, and the richest parts of the ore body also coincide with really high grades of fluorite and barite, over 10%. So this is an earlier stage. This is K feldspar and magnetite alteration, but again, the sodic calcic alteration is largely restricted to the breccias, and it's been so overprinted in the ore body that you can't really see it. This is what the magnetite apatite rich zone is. I mean, it's almost impossible to tell what this rock originally was because it's just these huge apatite crystals with magnetite and pyrite and carbonate. But so looking out to less altered equivalents, it appears to be the volcanic, Mount Fort Constantine andesitic volcanics. So we did some stable isotope work. We sampled quartz and magnetite from the pre-ore stage. We did this in the shrimp lab at ANU. So we did this in situ with paired analyses. And then we also did sulfate-sulfide paired analyses for the ore stage, barite and chalcopyrite. So this way we could use because we're doing isotope pairs, we can better constrain the temperature and the bulk sulfur composition. This is from the shrimp lab at ANU. So what you need to take away from here, the oxygen isotope signature from the pre-ore is 9 per mil, which is kind of a regional trend, which doesn't tell us a lot. I mean, it could be magmatic or metamorphic. It's a bit hotter at about 430 degrees C. And that overlaps with other deposits in the region. When we looked at the fluid inclusions, they're incredibly high salinity, over 50 weight %, heterogeneously trapped. So we can't really get true temperature pressure calculations from that. What was bizarre was that we didn't see much evidence for CO2, but these are definitely high salinity fluids. They're compatible with the magmatic fluid. A metamorphic fluid you wouldn't expect to be this saline. Looking at the ore stage, what was really shocking was that this is sulfur isotopes. So the orange is chalcopyrite, and then the bottom is barite. Obviously, the barite is more enriched, which you expect for the sulfate mineral. But what's interesting is we have this bimodal isotopic distribution. So E1 North is isotopically lighter, around 0 to 1 per mil, whereas E1 South is much heavier, between 10 and 15 per mil. And this bimodal distribution was present in both the barite and the chalcopyrite and the pyrite as well. And based on the isotopic equilibrium temperatures, we get a range of about 240 to 350 Celsius for formation temperature, so it's a bit cooler. When we try and back calculate the bulk sulfur composition, so normally when most isotopic values are presented, it's hard to, just looking at sulfide alone, it's hard to actually tell what the bulk sulfur composition of the fluid was because of all the effects of temperature, et cetera, on fractionation. But when you have paired sulfide sulfate analysis, you can get better constraints. And so at E1 North, we estimated the bulk sulfur was about +4 per mil, which does overlap with magmatic or porphyry values, but it was much heavier at E1 South, around +16. But really what's interesting here was that the sulfides and the sulfates, they co-varied, which does suggest a magmatic hydrothermal fractionation process rather than just pure fluid mixing. So the question is here, are these representing distinct parts of the hydrothermal system, a proximal component where the magmatic signature is versus a distal component that's dominated by external fluids? And then how does this compare to the fluid, the ore stage fluid inclusions? So we looked at barite because there is no ore stage quartz really. The inclusions are actually extraordinarily large and much lower salinity, lower temperature. So again, it's somehow we have to account for this huge drop in salinity from the pre-ore mineralization to these later fluids. So these temperate trapping pressures, there's a bit of uncertainty there, but they're fairly deep, which is consistent with Ernest Henry and most typical IOCG environments. So this comes back to the genetic model. So what you have is, your intrusion at depth, fluids migrating up these structures, and then from an external fluid migrating down the structures and mixing. And this is the magmatic center, if it existed, was probably centered closer to E1 North, where you have a dominant magmatic signature. And then more distally at E1 East and E1 South, you had a non-magmatic signature, which it's problematic as to where that's coming from exactly. And it's possible that that external fluid was contributing some of the sulfate, but it doesn't absolutely have to. So looking at the mineral system, this is from Julie Hunt's paper, and E1 North fits well within the hybrid systems. E1 East is clearly dominated more by a non-magmatic signature. And then you have these end-member magmatic things like Lightning Creek. So perhaps the best way to look at these is that you have a wide range of mineral system environments. You need some sort of basinal brine environment, and then there's a varying degrees of magmatic fluid interaction, and that is one way to account for the variety of alteration styles that we see in these systems. And E1 could represent a kind of an intermediate or a system where a range of these environments are preserved. So as far as looking at exploration, for E1, you need the right host rocks intersecting with structures to focus the fluids. The E1 North ore body, which is the largest and highest grade, does have the most magmatic-like signature. So that you might want to look for that in vectoring. And then some tools that have been shown to work in the Cloncurry region. Obviously, magnetics and gravity combined. You don't just want to look at magnetics because you'll hit the magnetite zone and not necessarily the copper. It's important to assay for barium and fluorine and phosphorus because these can be, these are major gangue minerals, and at least in the Cloncurry and Gawler Craton IOCGs, and they're not something you can just ignore. There's some preliminary data that I didn't include here, but others have started working already on apatite because it's so common in all of the systems that we've talked about today. But looking at halogen chemistry and apatites, how do the fluorine and chlorine ratios change? We had some evidence that there might be a shift in those ratios from proximally to out from the ore body. And as Christiana just presented, people are already finding alternatives for geochronometers. Monazite doesn't work very well. Titanite works, but it's usually pre-ore. So those are just tools I think that we should be working on. So that's all that I really had. So if anyone has questions, yeah.
Thank you very much, George. I think you've been on time. So
All right.
Great job. I think we have to move forward to Paul, and after that we can discuss and answer the questions at the end. Paul, fire off.
All right, let me get the screen on. You can see the screen all right?
All good.
Okay, so I'm going to zoom in into yet another deposit in the Mount Isa inlier. So thanks, George, for doing the introductions to Mount Isa. We're going to be looking at Tick Hill. Why Tick Hill? Because Tick Hill is quite an enigmatic, very gold-rich deposit that was mined very profitably and made a lot of money, but it has never really been studied very well. So GSQ came up with some sponsorship a few years ago to sponsor a PhD project, Tromley, and we've started up an additional master's student, Grace Manistar, to look at the fluids of Tick Hill. And here I'll be presenting some of the results from that and give you an overview of the Tick Hill deposit. And in the context, in that context, I'll come down to some of the genetic models as well. I'll conclude with that. So I'll give you a background and the geological setting and the various aspects of the Tick Hill deposits. And in the end, we'll have a brief discussion of what it might be. Right, so Tick Hill is in the Mount Isa inlier. It is in the central part of the inlier in a zone called the Mary Kathleen domain. And it occurs towards the southern part of the Mary Kathleen domain right there. It was mined over a short period of time between 1992 and 1995 by Carpentaria Gold. It produced 500,000 ounces of gold at a very high grade. 22 grams per ton was the average grade, but when they started mining it, it was even higher grade. It made a lot of money in a very short period of time because it was easy to process. It was all free milling gold, very low cost mine, which was actually the lowest cost mine, lowest cost producer in 1992. All the gold is native. It is almost no silver in it. There's very minor copper associated with it. And like I said, it's very concentrated and high grade. So with these characteristics, that makes this type of deposit a very attractive exploration target. But because it was mined over such a short period of time, very little research was done on the deposit. And once it was closed, people basically walked away from it for a long time, and little information is available. So Tick Hill is currently being mined again. It's been taken over recently, last year, and There's still a number of dumps there that contain gold that are being processed at the moment. There's a drilling program going on to discover any extensions to the mineralization of regional prospects. So what is Stick Hill has been the big question for a while. If you go through the literature, you'll find various suggestions of what it might be. Orogenic gold has been suggested because Stick Hill sits in a big shear system. IOCG, but if it is IOCG, it's a funny one because it has no copper. So here's a diagram from Groves et al. On his overview paper for IOCG deposits, and he places Stick Hill right there at the high end, high gold, very low copper end. There's been big debate whether it's early or late. When the exploration for further gold was done in the area by MIM in the 90s, they adopted a model where they assumed that the gold formed early on in the history of the mountain belt, of the Mount Isa terrain, during D1 extension, and that it was associated with igneous intrusions, but heavily deformed afterwards. Later work suggests that it was late, and if you read through the various company reports and exploration reports from the time, you'll find just about anything from epithermal to synth sedimentary to late hydrothermal to IOCG to orogenic gold. So there's a bit of confusion around the deposit. Now here's a list of the typical characteristics for IOCG deposits, and I won't go over all of them just in detail, but it's just summarized from Williams et al. And Groves et al. And we've already covered a lot of these aspects. Now what I'll do in the rest of the talk is just take you through various characteristics of Mount Isa, and then I'll come back to this table and we'll have a look and see how Tick Hill compares with typical IOCGs. So in terms of broad geological setting, Tick Hill is hosted by really high-grade metamorphic rocks that reach almost into granulite facies. We've done a lot of dating around Tick Hill to establish the age of these rocks. They were originally interpreted on the geological maps as 1730, 1740 Corella Formation. But all the ages we get for the intrusions and volcanics associated with the host rocks date them to anywhere from 1850 to 1770, 1780. And the direct host rocks are essentially mixed siliciclastic carbonate sediments that are about 1780 in age at upper amphibolite facies grade. If you look at the broad geological, or the structural setup, so we've got this terrain to the west, you got basement gneisses that are 1850. To the east, everything gets covered by younger sediments, Cambrian sediments. You got this relatively poorly exposed central bit of siliciclastic carbonate sediments, mostly calc-silicates and various types of schists. They are mononitic, they are strongly sheared, and they are repeatedly folded. So there's at least two major folding events. There's a large-scale structure with Tick Hill sitting on the eastern limb of this structure. This structure is referred to as the Tick Hill syncline, and it's a D2 upright fold that folds early mononitic foliations. And these earlier mononitic foliations have got intrafolial folds. Then everything is cut by two sets of shear zones, the red shear zones, which are very closely linked to the mineralization. We've called them D3, and they're normal folds. And then they cut by the orange shear zones here, which are later strike slip folds, and they cut through mineralization. There's not much displacement on them in the pit, but they do pulse-date mineralization. And in the third dimension, the mineralization dips to the west at intermediate angles, about 50, 55 degrees. And the ore body has a strong linear trend to it that plunges about 50 degrees, almost due west as well. If you look at the geophysics of the ore body itself is characterized by a strong magnetic low. So this is the great envelope spotted on top of the regional mag. The high magnetic highs you see over here is magnetite. So there's strong magnetite alteration, in particular in the hanging wall of the ore body. But that magnetite's replaced by hematite directly within the ore zone, and that shows you this strong magnetic low. If you step out a little bit and you look at a larger scale, you'll see this circular feature, which was spotted in the late 90s by MIM when they did the helimagnetics over the area. And that was interpreted as potentially a deep-seated intrusion that was underlying the ore body. Now, some of this, what you see over here, is actually this D2 synform, which is the magnetite-bearing quartzites, which are folded around. But this circular feature overprints that. Whether it is an intrusion or not, we don't know, because there's really no outcrop of any intrusion in the area, but it's an interesting thought. So let's zoom in a little bit more detail in terms of the host lithology. So this is the outline of the pit. It shows the ore envelopes again, with the orange being the 16 gram per ton envelope, so it's really high grade. With the quartzite units in yellow, which are over here, and the hanging wall quartzite, which is to the west, is very, very magnetite rich, and in places is almost pure magnetite. On either side, you've got mixed calcsilicate and amphibolite units with a few schists in there as well. Calcsilicate schists are both in the hanging wall and in the footwall. And the core of this structure is mainly biotite schist. There's biotite sillimanite schist in there as well as quartzofelspathic gneisses. And these quartzofelspathic gneisses in particular, I've shown two examples here, in particular are the host to the mineralization. They've been called galastone in the past, based on their pinkish laminated nature and the overprint by both the red hematite albite alteration and the green chloride epidot actinolite hornblende alteration that goes over the top of it. And it gives it the coloration of a galah, which is a parrot here in Australia, for those that are not from here. The mineralization, importantly, is not restricted to the galastone. So even though this is the most characteristic rock that people often have in mind when they talk about Tig Hill, it's actually cuts across the different lithological unit, and even sections of the quartzite and some parts of amphibolite are mineralized as well. So it's not just purely the galastone that hosts the mineralization. What is this galastone? Again, there have been past interpretations have varied from sedimentary quartzofelspathic sediments, sandstones, etc., to intrusives. The galastone has got the geochemical characteristics of it are exactly the same as what's called the Tig Hill granite outside of the pit. These are probably originated as migmatites. If you look at rare earth element patterns, they're fairly typical for low temperature migmatitic partial melts. They are leucocratic granites in composition, and they were dated at 1775 million years. There's plenty of zircon in these things, and we've dated a lot of it, and they give us a very well constrained age. So they're very similar to the Tig Hill granites outside of the pit, but inside the pit, they are mononitic, very, very strongly sheared, and they occur as fairly thin lenses that are strongly altered. In terms of the structural setting, this is what the pit looks like at the moment. It's filled with water, and part of the pit is collapsed, especially in the parts where there was mineralization. The old underground decline went in through this part over here, and it spiraled downwards. So part of this collapse is really the collapse of the decline itself and the ore body that was mined from underneath it. We've got historical photographs of the pit that tell us where the ore zone really was, and you can see the alteration systems here in the sidewall, and the high-grade ores sitting in particular here where they're currently digging things up, which corresponds in the current pit over here. All right, so quickly going through the most dominant structural elements in the pit. So it is a high-grade gneiss that is mononitic. It's completely recrystallized and strongly altered, and much of the feldspar is replaced by albite. So although the macroscopic texture is still fairly much the D1, D2 texture, what we're actually dealing with is blastomelanite or recrystallized melanites of an older age. If you plot them up, the foliations are domainal. There's two major directions in which the foliation trends. There's a strong mineral lineation here in red, The mineral lineation does not coincide with the mineralization, even though, again, in some of the older reports, it was suggested that that earlier mineral lineation controlled the long axis of the mineralization, but that's not the case. This is overprinted by faults. The most important set of structures or faults is these red ones. There's two sets, north-northeast trending ones and east-west trending ones. This north-northeast one, trending one, is actually located along an early foliation truncation plane. So during the early deformation, the foliation is domainal, like I said, and there is a zone which demarcates a sudden shift in that foliation trend. And that's an early foliation truncation plane, and that's being reactivated by these D3 shear zones. And that clearly controls the distribution of the ore mineralization as well. That is cross-cut by a series of east-west faults. And if you were to plot up the lower grade envelope, so that a 0.1 grams per ton envelope, it will actually run along these east-west faults as well. These east-west faults have characteristic metasomatic halos around them as well that weather out nicely in the upper parts of the pit, and they're characterized mainly by feldspar, mostly elbite and quartz. And there's also intrusions associated with especially this shear zone, where you've got series of pegmatite intrusions with uneschonal quartz vein intruding into it. All of these structures are indicative of normal faulting. So if you look at the pit walls, you can see these veins with metasomatic margins and pegmatites intruding in almost vertical uneschonal arrays within this major mineralized zone, indicative of a normal sense of shear. There is a lineation associated with these things as well, so it's actually normal sinistral, this major shear zone. And then there is east-west shear zones coming out as well. I'll show you a photograph of that in a moment. And the east-west and the northeast trending faults intersect, and that intersection lineation is absolutely parallel to the long axis of the high-grade mineralization in the pit. So in other words, the mineralization is strongly structurally controlled, and the main structural control of mineralization is this D3 faulting, which is normal faulting. It's associated with pegmatites. These pegmatites are dated at 1522, lots of zircon in these pegmatites, some really well-constrained ages coming from that, and that would suggest that the mineralization is around 1520, 1525 million years old. So late Eisen orogeny. All right, if you look at the northwest wall, you can see all these these east-west trending faults in that pit face over here that's collapsed. If you map that out, it looks like this. They're normal faults. Some of them are associated with breccias that have developed along these faults. These breccias, these are blocks from deeper down the mine that were just lying right over here that have been dug up. But these breccias have a matrix of quartz and feldspar associated with them. And they're associated with strong chlorite, actinolite alteration as well. And like I mentioned, it's these faults together with these northwest faults, the intersection of this, that seems to control the mineralization. And if you look along these faults, they've got these metasomatic halos. You see them in drill core as well, closely associated with the mineralization. And again, ages for these things are 1530, confirming what we thought from the pegmatites as well, that the age of mineralization is around that age. So let's look at the alteration. First of all, the regional metamorphism is an upper amphibolite, lower granulite fascious assemblage with K feldspar, quartz, biotite, sillimanite, and migmatite in the metapelites. Quartz feldspathicite gneisses are strongly sheared with nice, sometimes asymmetric porphyroclasts. And in some of the mafics, you've got hornblende, clinopyroxene, garnet, plagioclase assemblages. So we're looking at typically something like 680 and 6 kilobars as the background temperature, which was achieved during D1, D2. That gets overprinted by the alteration systems. So this is done by Trong. He's relocked many of the drill core to get this section done. You've got distal clay alteration, which are various smectites, illite, with chlorite and some hematite. And as you move into the ore zone, you start seeing initially a lot of magnetite, especially in the hanging wall quartzites. There's a zone that is extremely magnetite rich together with chlorite, epidot. There's also a little bit of hornblende actinolite in there. And as you move into the core of the ore zone, it's strongly albite, chlorite, epidot altered. Some lithologies contain low aluminium hornblende and actinolite margins as well. And there is biotite and cerussite, which seems to be texturally late, which in part is overprinted by a late second stage chlorite as well. Right, so looking in a time sequence, what you see is pre-gold pre-gold alteration, different stages of syn-gold alteration, and then there is post-gold alteration. Now, the pre-gold alteration is very much characterized by a lot of albite, which is a regional alteration that spreads well beyond the pit and goes for miles and miles and miles. In fact, it's everywhere where you look. There is a lot of magnetite, especially in the hanging wall of the ore body. Low aluminium hornblende and epidot are very common. Then as you go into the syn mineralization stage, albite is very prominent, and hematite, which replaces magnetite. The hornblende becomes less aluminium rich and turns into actinolite. The epidot loses its ferric ion and becomes clinozoisite. There's biotite, locally a little bit of K feldspar as well, and increasing amounts of cerussite as well as early chlorite. And then there is a later stage, which is also syn mineralization, where you see more K feldspar, hematite still very prominent, but cerussite starting to take over. So you're moving from more sodic calcic alteration into more potassic alteration. Characteristically, very, very, very little sulfite in all of these phases. There's a few spots where you do have sulfites, but in general, there's almost no sulfite at all. And then there's a late phase characterized by calcite, calcite veins, bismuth, tellurite, copper selenites, and sulfites as well. So you get sulfites of copper, a little bit of arsenic, a little bit of nickel cobalt, and quite a lot of bismuth and selenium. Characteristic with this alteration are these core axis parallel fracture systems along which all the alteration takes place. And those fracture systems actually correspond to those east-west faults, those D3 east-west normal faults that I showed you earlier. Right, so simplistically, if you just look at the trend of this pre-syn and post-gold mineralization, the temperature at the pre-stages where you still have typical epidot chlorite amphibolite assemblages would be around 550. We haven't done the exact thermobrometry yet. And as you move down towards the end, you get the various selenites that actually start coming in with the gold fairly late in the paragenetic sequence. But you got tellurites and selenites with bismuth, which typically form at 200 degrees or lower temperatures. So you see a drop in temperature. You see the oxygen fugacity go up at the mineralization stage with a lot of hematite forming. You see the sodium dropping off, the sodic alteration, and you see the potassic alteration going up. So a few more things on the metal zonation that we observe. Now, it is gold only. There is really very little copper in this deposit, but there is, if you put 100 ppm envelopes in, you will see a Fuchswald copper anomaly that sits directly below the deposit. There is a little bit of a cobalt anomaly as well in the core of the deposit, but there is also copper in some of the hanging wall lithologies, and half the time we don't know whether we're just looking at copper, cobalt, nickel anomalies in the host lithologies, mainly the amphibolites, because there's a close correlation with the amphibolites and those elements, or whether it's got something to do with the mineralization. Now, during the exploration in the 90s, there was a lot of geochem done for these elements, and if you look at the historical assay data, At the 1 meter scale, there is zero correlation, or there's generally zero correlation between copper, cobalt, and the gold. So on a broader scale, yes, there seems to be a copper footwall alteration zone, but on a detailed scale, that correlation is not obvious. What you do see is often very skeletal chalcopyrite in thin section. You also see skeletal pyrite that seems to be partly dissolved and redeposited in other parts of the deposit. So it may well be that the copper or that the gold may have replaced host rock chalcopyrite, which is then transported to the periphery of the deposit, giving you a copper rim. Some interesting textures. This is hot off the press. Tron's been on the SEM the last couple of days taking some photographs, but it shows you a few things that are interesting to point out. The gold is very clustered. You've got very coarse grained gold, which is millimeters in size, which is often surrounded by halos of much finer grained gold. But all the gold is free gold. It's not usually not sitting in sulfides. Now, although I show you photographs here of sulfides, there is only very, very few spots where we find sulfide associated with the gold. Gold is usually free gold with a granoplastic texture like this, included in albite, included in quartz, included in hornblende. So it's part of this monazite texture, this recrystallized monazite texture in many places, but it does get recrystallized at a later stage and forms these halos of much finer grained gold as well. You see it often in association with bismuth selenites, so like in this photograph, or you see it in association with selenium-rich pyrrhotite. And again, there is bismuth selenites associated with it as well. And here's an example of 2 generations of pyrite. You got early pyrite that doesn't seem very happy at all. And then you got later pyrite, which is selenium-rich that overgrows and that comes in later. So multiple generations of sulfides, multiple generations of gold, and a lot of selenite and very little sulfur in the system. Another thing you see is that the gold itself is often associated with microfractures. So even though you're dealing with granoblastic gold that sits in the cores of grains, so we've got examples where gold sits in the core of what we think is peak metamorphic CPX, clinopyroxene, but it's probably due to microfracturing. The gold is clearly moving along these microfractures, which again can be linked ultimately to these east-west fracture systems we see cutting through the mine. So a few quick comments about the fluids. This is ongoing work that Grace Manastar is doing, but the fluid inclusions that occur within the quartz that occurs as rims around the gold it tends to be water only. There's very little CO2 in these inclusions, if any. Many of these inclusions have no CO2 at all. They got highly variable vapor bubbles in there. It looks like a boiling system, or there's a phase separation going on. They're very, very saline, very high halite. There's also hematite in many of these inclusions. And there is other salts in there as well. We don't quite know yet what they are. They're probably calcium salts of sorts. But it's noticeable that there's an absence of CO2 and methane in any of these fluid inclusions. So very watery inclusions. There is late carbonate alteration as well, and the carbonate overprints the mineralization. With the carbonates, we get the sulfides coming in, and these fluids too are actually very similar, and they HDR, hypersaline hydrous inclusions. So these saline fluids have been around and seem to be quite widespread both in time and space. If you look at oxygen isotope work, so we got some oxygen isotope work which was done for all the different generations of quartz. So there is early quartz, peak metamorphic quartz. There's quartz which is associated with the alteration and that envelops the gold. There is quartz that comes in relatively late. What is striking is that most of the oxygen isotope values are very, very similar and fall within a very narrow range, which is the same range that you get in the Mary Kathleen domain, which was documented by Nick Oliver in the mid-90s, where it's been associated with this regional albite alteration, sodic alteration that occurs in the area. So you can see that we've got the exact same values over here. At times, there is a few heavier oxygen isotope values there, which are characteristics for the calcilicate units that have been described in the Mary Kathleen domain as well. So it's basically this group. Very little evidence for light oxygen isotopes. There's one or two associated with the pegmatites. So it's a very homogeneous fluid that seems to go in, or it's a very large fluid reservoir that whatever mineralizing fluids moved into. So if you look at all of this and you compare it with what a typical IOCG would have looked like, so Tick Hill contains almost no copper, and the copper that is there, it's uncertain whether that's background copper that was originally contained in the amphibolites, because there's a fair bit of chalcopyrite in these amphibolites, or whether it was copper that came in with the mineralization. It's clearly structurally controlled. It's got abundant magnetite, especially in the hanging wall, but the ore body itself is associated with hematite. There's not much titanium in the magnetite and the hematite, but we need to do more work on that. No clear spatial association with intrusions, although, you know, the geophysics, as I showed you, shows a hint that there could be something there. But the age of the mineralization, 1522, coincides with the Williams batholith. So on a regional basis, there seems to be a broad spatial association with a major intrusive event in the late Eisen. Clearly associated pervasive alkali, mainly sodic albite alteration, as well as calcic alteration with epidot. There is late state carbonates, which we see at Tick Hill as well. In terms of the metal association here, it's a little bit different from a typical IOCG. We do see a little bit of nickel, cobalt, and copper kicking around, but like I said, not clear if that comes in with the mineralization, but clearly there's a lot of bismuth, selenium, and a little bit of tellurium around as well that comes in together with the gold. Depth of formation, it's probably less than 10 kilometers. Already mentioned the alteration systems. The fluids are brines, hydrous brines, very little CO2 in this case. Where do the brines come from? God knows. People have suggested a magmatic source, but it's probably some sort of fluid mixing that takes place here. Possible mixing of sulfur-poor metal-rich brines with sulfur-bearing fluids at sites of deposition. That's what the models say, and that seems to be possible in Tick Hill as well. So like what George was saying in the previous talk, Tick Hill also appears to have an element of fluid mixing associated with it. This is the last slide. So this is a paper by Skiro and Walsh from the Tennant Creek area, where you've got a lot of bismuth, selenium-rich, gold-only or very, very low copper ironstone hosted gold deposits as well. And they've got many, many similarities with Tick Hill. And there they've been explained as the result of fluid mixing between reduced and oxidized fluids of both basinal and possible igneous origin. And depending on the relative dominance of one fluid over the other, you may have copper-rich end members and gold-rich end members. And Tick Hill seems to have many of the characteristics of the gold-rich end members of these Tennant Creek deposits as well. There's one big difference though, that the host rocks in Tennant Creek are quite low-grade drenchist fascious sediments, whereas at Tick Hill, obviously, they are these high-grade mannanites. But don't be fooled by these mannanites. They probably have got nothing to do with the mineralization at all. So thanks very much, and thanks to GSQ for sponsoring this project, and MIM for providing a lot of data, and Nick and Roger for giving us the samples, and Carnaby Resources, who have started mining the deposit again earlier this year, for giving us access to the pit and to the drill core. So thanks very much.